we took the notes last day. We're going to do states of matter here. So real quick, states of pure substance, solid, liquid, or gas depends on intermolecular forces. How well this molecule is otherwise, right? These forces can be, how do you hold stuff together? They can be ionic, okay? They can be metallic, they can be molecular, they can be more specifically across molecular, they can be highly contact, dipole, and London forces. Okay? In solids, the attractive forces are relatively strong. They have to. If you're going to hold a bunch of stuff together, I'm going to show you a diagram here in a few minutes here. But if you want to hold stuff together, those are intermolecular forces that hold each other together have to be very, very strong. Okay? So in solids, they're going to be quite strong. Liquids, of course, are weaker. Gases, probably obviously the weakest. Yes. If you add energy to solid form, for example, a solid, some type of solid, you can give those molecules, particles enough energy to start moving. And if they start moving, they will eventually break some of these molecular bonds. And when that happens, you're going to get changed from a solid to a liquid. And if you keep heating it up, you're going to eventually change that liquid. You're going to break enough of those intermolecular forces to get gases. So if we have solids, you can add energy to break them into liquids, and you can add energy to break them into to get gases. All right? Once again, to break it from a solid to a liquid takes energy. You have to give particles enough energy to start to move and break intermolecular forces, intermolecular bonds. And that's what we talk about here. By the way, let's go back up here for a second. I asked the other classes here, if we're talking about breaking ionic forces here, we're obviously talking about possibly breaking up some of the plus minus, yes? Ionic is metals, nonmetals, gain, lose, yes? Plus minus, sodium, positive ion, chloride, negative ion. What type of structure is sodium chloride or ionic compounds in? What's that structure called? You should know this. Ionic compounds always form that cubey looking thing. What's it called? Yep. Nope. Yep. Nope. Ionic. Metallic bonding is positive ions in a sea of electrons. What does ionic always form? Remember that cube shape we had up here on the diagram? It was plus minus. All the positive attracts all the negatives attract all the positive. What's that thing called? No. Huh? Starts with that. It's a ways back. CR is the first. CRY. Yeah. You betcha. Crystal lattice, right? Always form a crystal lattice. Make sure you guys know that. All right? The temperature where you change a solid to a liquid is called the melting point. So if I ask you to define what is the melting point, you would say where it changes from a solid, the temperature where it changes from a solid to a liquid. If we're going to talk about boiling points, of course we're going to say, well, what's the temperature that it changes from a liquid to a gas? Okay? Et cetera, et cetera. Now we're going to skip that. So here's an example here. We have, this is what I'm talking about. If we look at a solid, they're all locked together here. Look, down here, okay? This is all locked together. There's no free space. They're all locked together. All these red things I'm drawing are intermolecular forces, and those intermolecular forces have to be quite strong. They are holding that solid together. No motion, okay, really. They vibrate back and forth a little bit, but there's no motion. They're not free to roam around. If you think about it, what does a liquid look like? This is the liquid part here, okay? So we got some connections here, okay, like that. Look, there's a big empty space here. There's a space here. There's a little bit of space here, a little bit of space in there, and a little bit of space in there. So you get some spaces in between some of those molecules, okay? Liquids have the ability to change partners, we say. So if you think about water sloshing back and forth, there has to be some room in between there, in between those molecules, to basically change partners, right? So as it sloshes back and forth, these two are attracted to each other. As it comes back closer together, perhaps maybe these two are attracted to each other. But they're able to slide back and forth. They have some range of motion. Gases are, this one's tough to see here. Gases, okay, are free. They're free to move around, and they move around. In fact, that's going to be our next unit, is gases. They're free to move around within this container, or they're free to leave the container. And make no doubt about it, if these two molecules of gases here are close enough together, there will be an attraction between them. Okay, so there still is an attraction, but there's not enough attractions, or that attraction's not strong enough to keep it together as a liquid. Okay, they're kind of free to do their own thing. All right, so that's the three states. Everything relates to those three states here. And we're going to talk about melting and boiling points now. And one of the key things, first thing we need to talk about is metallic, okay, metals and metals like sodium, 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 positive ions and a sea electrons, and ionic compounds, opposites, plus minus, plus minus. By the way, these are both opposites attract, yes? Positive ions in a sea of electrons, positive ions attracted to electrons, positive ion, negative ion for ionic, yes? Opposites attract for both of these, okay? Opposites attract have the same, roughly about the same magnitude of melting and boiling points, how well stuff sticks together. They are both quite strong, okay? I'm going to show you how strong they are shortly here, okay? So these are both quite strong. Comparatively speaking, molecular compounds, when I say molecular, you say, let's play the game. Molecular, what? Yeah, sharing. Non-metals, yes? All that stuff. When I say molecular, you say non-metals. When you say non-metals, you say sharing, right? Weak. Sharing's weak, all right? So, these are sharing, these are opposites attract. These are strong, weak. Sharing weak. Terminator. Arnold. Don't make me go there. All right. So sharing is quite weak. All right. So we have quite a big divide here, and I'll show you that coming up here. We're not going to do this. Don't worry about that. Or that's a little bit more. I'm not going to worry about that. Okay. So I thought I'd erase this, but this here. Okay. Now what this page says is the following. Okay, and you don't even have to read it over. I'm going to summarize it for you. Listen. In nonpolar molecules, if I talk about nonpolar molecular compounds, when I say nonpolar, you say, you had a quiz on it on Friday. Nonpolar says, yes, what? London, yes? So when I say nonpolar, you say London. Sharing, yes? Etc., etc. London forces are based on two things. What are they? Quickly. Yes, but there's two things specifically that London forces depends on how strong they are. Two things. Yeah. Yes, size and shape. Size and shape are the two things that affect London forces. Make sure you know that. Okay. So what they're saying here in the first paragraph is basically the more electrons you have, as the size increases, the attractive force, the melting boiling points increase. Okay, think about this for a second. Nonpolar London forces, think HH for example. And you got electrons going around and around. The more electrons you have going around and around, the more temporary distortion you're going to have. The more temporary distortion you have, the more attractive forces you get, the more London forces you get between molecules. And the more London forces you get, the stronger it's going to be. And the stronger it is, the higher the melting or boiling points, the more energy you're going to have to put into it to break those London forces. Okay? The strengths of intermolecular forces are what hold them together. The more energy you need to break those forces. Okay? So we'll talk about that in a second. So that's what they're talking about in the first paragraph. In the second paragraph, it says in polar molecules, basically the same thing applies. Why? In polar molecules, we think about dipole-dipole and hydrogen bonding, yes? Let me ask you this. Water is an example of hydrogen bonding. Does water have London forces in it? Yes or no? Yes. All molecules have London forces, yes? True? Do all molecules have electrons going around? Yes. So they all have London forces. So what they're saying here is, in a polar molecule, guess what? London forces is still a factor. Size and shape. The more electrons you have going around, the bigger, the more distortion you're going to have. The more distortion, the higher the melting boiling points are going to be. The stronger that London force is going to be. Okay? Here's an example of some melting and boiling points. So let's talk about this for a sec. I drew a red little line here. You don't have to do that. But I drew that just to kind of show you. Look, if you think about melting points, okay, metals. So metals here, things like lithium, 181, aluminum, 660. I mean, lithium, for example, 181, you could probably take lithium home and put it on your stove and you could probably melt it. Yes? 181 degrees Celsius. Maybe the same with tin, 232. Put it in the oven, you could probably melt it. Aluminum, probably not. 660. Silver. Hey, G, how's it going? So I usually say in the staff room. 962, for example. Some of you guys may not get that joke. AG, how's it going today? 962, okay? Copper. 1085, that was a cop car. 1085, okay? Takes quite a bit of heat to melt those things. 1,085 degrees Celsius, probably need about 3 ovens put together to get that kind of heat to melt it, okay? Look at their boiling points. Oh my goodness, 1342, 26. That's what we would call probably hot. Takes a lot of energy to boil that stuff. Takes a lot of energy to melt it. Why? Because opposites attract, hold each other together very well. Metals, positive ions in a sea of electrons, yes? Lots of opposites attract. Look at ionic compounds. Opposites attract. 636, 661, 714, 801, 2825 just to melt magnesium oxide. My goodness. That's a lot of heat. Okay? And then look at the boiling points here. Very, very high. Takes an incredible amount of heat to break intermolecular forces. In this case, ionic. In this case, metallic. Yes? So, which one of these two is stronger? And the answer is they're comparatively about the same. Okay? Metals are not necessarily stronger than ionic, and ionic's not necessarily stronger than metals. They're both up here. They're both really strong. Look down here. Molecular. Look at the molecular compounds. Some of these you can't even relate to, maybe, perhaps. But look at chlorine gas, for example. It melts at negative 101 degrees Celsius. It boils at negative 34 degrees Celsius. It boils outside, basically. It's a gas outside on a cold winter day. It's already a gas, okay? Think about, if you don't understand that one, think about water, okay? Look at these numbers here. 661, 801, 2825, 1085. Look over here. Look at water. Sharing electrons. Molecular. 0 and 100. Okay? Comparatively quite weak, yes? Look at the difference in numbers. Molecular compounds are pretty weak. In fact, look at this one here. There's another C, I think that one's, I don't remember that one, C6H6O, 6 and 80. Okay? Pretty small numbers when you compare them to the top ones. Why? Because you're sharing. Yes? Molecular. This one here, I think that's glucose. Glucose, you might say, that's pretty decent, 142. But it can't even stay together. It simply decomposes. What does that mean? you can't even turn glucose into gas. When you heat up glucose, it actually changes into, well, it first changes into a liquid. After that, it changes into carbon, hydrogen, oxygen. It just simply decomposes into the 3 elements. It can't even stay together, let alone stay together in gas form. Okay, it just simply decomposes. So look at these numbers. Very, very strong, pretty weak. Yes? All right. We're going to go on to a chart here. Nope. Let's get rid of that. We're going to get you guys to do some drawings here. Now, on your page, you will have, let's see here. You will have strengths of summary of forces here. I don't want you to put it in that square. Leave that square blank. Underneath the square, though, or on the next page is fine, at the back, you guys can draw some diagrams for me here. Here we go. I want you to draw the following. CH4, SiH4, GeH4, and TinH4, SnH4. I want you to draw those for me, however you want to. Well, and we'll go over those shortly here. I'll start with this one here. CH4, molecular, obviously, yes. SiH4, GeH4. Oh, wait a minute. Who drew GeH4 like that? Put your hands up. Let's see. Come on. Don't be shy. Who drew it like that? Who drew it differently? Who drew this? Who drew that? Hey? So which one's right is the question. So, here's the deal. Some people are like, what the? Why'd you draw that? Some people are like, you shouldn't draw that. Look, where's GE? It's on the left side of the periodic table. It's on the left side of the staircase, right? So that implies it's a metal, yes? And H, therefore, would be the non-metal, I guess. Is that correct? So you maybe should be showing transfer of electrons, like so. True? I won't tell you yet. Just wait. So that's why people are drawing them like this. They want to show the transfer of electrons because it's a metal and a non-metal, yes? And I would say, hey, you know what? Good for you. That means you're thinking. You're not falling into the trap like CH4 and SiH4, GeH4, and stuff like that. So I applaud you for that. That's good that you're thinking that you're not just saying, oh, they must all look the same. Unfortunately, you're actually wrong, but that's okay. Here's the deal. This one here, hydrogen's 2.2. If we actually take a look at electronegativities there, and that GE is 2.0, is H going to have enough power really to steal that as an ionic compound? Probably not. Okay, probably more of a sharing thing here. In fact, those two are pretty close in electronegativity. Now, if that was, for example, well, I'll say that in a minute. So probably more molecular, I would think, actually, with this particular one here. So actually, if I was drawing this one, good for you if you drew this, because you're kind of thinking outside the box a little bit, and that's good. But I would say it probably tends to look more like this here. And you know what? I know you don't have another piece of information, and I know that, but I will prove it to you in a little bit of time here, okay? That in fact, GeH4 is probably, in fact, more molecular. Don't forget as well, GE is technically a metalloid, yes? So it's got properties of metals and nonmetals. Which one is GE behaving with hydrogen? In this particular case, it's probably more molecular sharing, okay? Now, having said that, if I switch hydrogens out for Fs, 4.0 and 2.2, I would hope that you show me ionic, yes? Because that is most certainly a big enough difference, right? 4.0 and 2.0, that's 2.0 difference. Are they going to be sharing electrons? No, no way. Okay, or yeah, they're not going to be sharing. They're going to be giving and taking. Okay, so in this particular case, I'd probably go with that drawing there for this particular one. And you know what? SNH4 is no different. It actually has the exact same electronegativities here as well. Okay, and the reason I picked these is because these four have some stuff that's in common. Okay, all right. Any questions on that? Now, next. What is the general formula for this one, or these ones, CH4? What's the general formula for this? Molecular, so you should be thinking general formula, AX4. Do you agree that all these have AX4 then? Yes? Okay, so what kind of shape is that? Well, I kind of say spherical, yes? Okay, you could say they have a kind of a spherical shape. Yes? Kind of looks like, you know, roughly something like that there. AX4, what kind of molecule? This is the next important part. And you need to be able to compare these, because at some point, I'm going to say, arrange these four molecules from lowest boiling point to highest, or lowest melting point to highest. AX4, CH4, what kind of molecules are these? Are these polar or non-polar? Since we're talking about molecular. Actually, let me do this, sorry. Let's start here. Are these ionic compounds? Are they metallic? Are they just metals? No. Are they non-metals? Non-metals. So therefore they're molecular, yes? Are they hydrogen bonding? Do you see any hydrogen bonding here? No. Are they dipole-dipole? Which implies they're polar, by the way. Are they non-polar molecules? AX4, all X's are the same, therefore they are non-polar, yes? True? London forces. So these are non-polar. And in fact, London. Okay? London forces are based on two things, size and shape. We already talked about the shape, kind of spherical. They're all the same. What about the size? Well, here's what we need to be able to do. We need to be able to count up some electrons here. Okay? Remember, not just valence electrons, all the electrons. So CH4, C is number 6, 6 protons, 6 electrons. Each hydrogen has 4 electrons. So that's a total of 10. Yes? 6 for carbon, 1 for each hydrogen, 4, 10. This one here, add them up. 14 for silicone and 4 more, 18 total. Germanium is 32, and 4 is 36. And tin, SN is 50. That's my gangster 50. And 4 is 54. 50. Yo, yo. 54. Guess what? We picked these 4 molecules for a reason. Look, they all have the same shape. They're all non-polar. They all have London forces. They're all AX4 tetrahedral. They're all non-polar, London. Okay? So what's the only difference between these two, or between these 4, I should say? Size. The only difference. And we know that, look, as size increases, melting points, boiling points increase as well, because, look, 54 electrons. Better chance of distortion? Yes. More distortion, more London forces. More London forces, more attractiveness between molecules. More attractiveness means they stick together better. How are you going to break those apart? You're going to have to put more energy in to break those apart. You're going to have to put in more heat. So the melting points and boiling points increase. Yes? Those are all linked together. So we say increase in melting points or boiling points, depends on what we're talking about. Really, they're not the same thing, but if the melting points go up, usually the boiling points go up as well. Okay? Those things are all related to each other, right? How melting points and boiling points are a direct measure of how strong molecules are. Which one's the strongest? Well, obviously it's the SNH4. Okay? If I what you're going to have on your test is this. I'm going to label these 1, 2, 3, and 4, for example. From weakest to strongest. Which one is the strongest would be 4. Which one's the weakest would be 1. So in this case here, you go 1, 2, 3, and 4 would be the strongest. Okay? So you'll have to rate those. That's a numerical response type of question. Or I could give you a multiple choice question. These 4 compounds, which one is the strongest, A, B, C, or D? Okay? This one is the strongest because it has the most electrons, most distortion, most Ionic forces. Therefore, it's got the highest melting boiling points. Okay? Are we clear? Any questions so far? Yes, no? I think there is, but okay. Now, look, I'll prove it to you. Here, go back to this chart. You guys have this. Okay. How do I know that GeH4 and TnH4 are not ionic? Look, where's their boiling points? Not even their melting point, the boiling point. Look where it is, guys. The boiling point at TnH4, okay, is right here, -50. Does that sound like an ionic compound to you? Probably not. Ionic compounds, boiling points, probably thousands of degrees Celsius. 800, 900. This one is -50. It's already a gas. Okay? So this is most certainly probably not behaving as an ionic compound. In fact, it's not. The electronegativity difference is not enough for it to happen. Okay? Now, we're going to do another example here. Let's do this one. NH3, PH3, ASH3, and SBH3. Go ahead and draw those, okay? And we'll talk about those in a sec. Okay, now listen closely. I kind of screwed this one up last time here. Seemed to do it fine other classes. So we're going to draw them out. We're going to say, hey, look, these are all AX3E, aren't they? Yes? True? We can talk about they're all trigonal pyramidal. Yes? Trigonal pyramidal. They do still kind of have that spherical shape to them, okay? Because those lone pair take up a little bit of spot there. So still spherical, but they all look the same, okay? Let's go through the list here. Is it ionic? Are these compounds ionic? Any of them ionic? Because if, you know what? If you got a compound that's ionic, guess what? It's probably pretty strong, yes? Or if it's metallic, it's a bunch of metals, probably pretty strong. Is this ionic, any of these? Metallic. Non-metals, molecular. Yes. So then we go to, is there any hydrogen bonding up here? Yes, this one. So you're going to write that down. Okay? Is that it? Is that all the hydrogen bonding we have? Yes, it is. Okay? Is there any dipole-dipoles up here? Once again, you have to understand whether the molecules are polar or non-polar. Are these molecules polar or non-polar? Polar, most certainly polar. They got a lone pair, AX3E. E tells you they're polar. When you're told that they're polar, you got hydrogen bonding or dipole-dipole, yes? This is hydrogen bonding. This must be dipole-dipole, dipole-dipole, and dipole-dipole. Okay? Now, having said that, okay, which force is stronger, hydrogen bonding or dipole-dipole? You should know this. Hydrogen bonding or dipole-dipole? What do you think? Which one's stronger? Hydrogen bonding is stronger. So we would say probably that this is the strongest one here. Okay? Out of those 4, I would tend to believe that that's probably the strongest one. Now, is it? Well, I guess we'll kind of see eventually here. What about these 3 here? This is dipole-dipole, dipole-dipole, dipole-dipole. Well, which one's strongest? I don't know. But guess what? We're lucky because every molecule Now, if these three are all the same, we can always revert back to, these are also all have London forces in them as well, yes? And of course, London forces are based on two things, size and shape. Well, the shape's all the same. We've talked about that already. So what is the size of these? By the way, I'm going to write down the size of this one here. Nitrogen 7 and 3 is 10. Trust me, I'm just running out of time here. 36 and 54. Okay, are the electrons there for those. 10, 18, 36, and 54. Now, I know I probably don't have to do that with hydrogen bonding, but I just want to show you something later on here. Look, based on these, don't worry about the hydrogen bonding one. Skip that NH3 one for a second. Just focus on these three here, right? If you focus on those three, does it make sense that boiling point or melting point would increase as you move across here? More electrons, more distortion, more distortion, more forces, more forces. The more forces you got to break to basically melt those or boil those. So once again, increase in melting boiling points as we go that way. Okay? So I would expect, if I looked at those three, I'd expect the trend to go like this kind of thing, right? Now, which one's the exception to that? Well, NH3. I'd expect that one to be the strongest because it's hydrogen bonding. So let's take a look. Okay. Now we actually happen to have these, and I'm going to do them in red here. Here's NH3, PH3, ASH3, and SBH3. Okay? So that's the trend, that's the chart that I'm looking at, is the red one there now. So, don't worry about NH3 for a second. Do you agree? Look, what explains this PH3 here, ASH3 and SBH3? Well, it's number of electrons. Do they increase as you go along? PH3, ASH3, SBH3? Yes. Boiling points and melting point, well, this is boiling point, so they tends to take off, yes? More electrons, more stronger force, etc., right? Look at NH3. It's higher than this one here because of hydrogen bonding, yes? I guess the question is, though, is NH3 the strongest force in that group of four? What do you think? Is NH3 the strongest one out of those four? Turns out it's not. Look, if you draw a straight line across here, what is that, minus 30-ish? A straight line. Turns out SBH3 is actually a little stronger, yes? That's a straight line, don't even start, okay? Seriously. Turns out SBH3 is actually stronger, yes? So, maybe I'm lying to you. Maybe hydrogen bonding is not stronger. Well, guess what? It's not stronger in this case. And I don't expect you to know this, but what I'm trying to tell you here is a couple things. First of all, hydrogen bonding is not always stronger than dipole-dipole. It depends on many factors. Like size, for example, is one of the factors. Does hydrogen bonding, does it still have London forces here? Sure it does. Every molecule has London forces. Turns out that there's only 10 electrons here. Guess what's happened? This last one, SBH3, has 54. Those 54 electrons, right, there's so many electrons going around and around, SBH3, there's so much distortion with that, it's actually holding the molecule better together better than NH3 is. Okay? NH3 is not as strong as SBH3 because of the sheer number of electrons, really. Now, having said that, hydrogen bonding still counts for something. We'll talk about that later here. But it turns out that SBH3 is actually the strongest one here. Now, would you know that? And the answer is no. Unless I gave you the chart, you would not know that. That's almost one of those trick questions. I would never ask you that. All things being considered equal, which one is stronger, hydrogen bonding or dipole-dipole? Well, it's hydrogen bonding. But here's an example where, and this happens often, where there's exceptions to the rule. Hydrogen bonding, turns out, is not stronger than SBH3 in this particular case, NH3, SBH3, just because of London forces, number of electrons. Okay? So this is kind of an exception in this particular case. We're just going to do one more though, and I want to show you just one more real quick here. We're going to do H2O, H2S, and this will be our last one, H2SE, and H2, oh, this one's my favorite, H2TE. All right, you guys draw those, and we'll talk about those in a minute. Okay, there we go. So they've now drawn for you. We can see that these all, once again, have the same shape, and there's a reason for that, because we're trying to compare them, trying to get you to understand that what the factors are that affect melting and boiling points. These are all AX2E2. Are these all polar, by the way? Yes? Oh, absolutely, because they got E in the formula, so they're most certainly polar. If you try to tell me water's not polar, well, that's not true. It's polar. We should probably start at the beginning again, though. Is it ionic? Are any of these ionic? No. Are any of these metallic? No. Are these nonmetals sharing electrons? Most certainly they are. Molecular compounds. Is there hydrogen bonding in any of these? Yes. Here. Yes? Water has hydrogen bonding. H bonded to N or F, in this case O. These are most certainly polar, so we talked about that. Dip, 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 dip. Yes? Okay. Now, which one's the strongest out of these? Well, if I asked you this question, I would say probably water is. So I would say this is probably the strongest. Okay? I know what you're thinking. That's what I told you last time too, and it turned out to be false. Well, guess what? It's not false this time. Okay? So, if I ask you this question, it'd be something along this line, where I expect you to say that hydrogen bonding is stronger. Okay? H2S is dipole-dipole, H2SE, H2TE. They're all dipole-dipole. That's not going to help us solve that, so we have to go to London. And if we're going to go to London forces, it's based on size and shape. So once again, let's count some electrons here. Oxygen's got 8 total electrons, not just valence, total. Hydrogen's got 1, so that's 10. This would be 18, 36, and 54. Now, they don't always follow that pattern, so just be careful, okay? But the ones we pick in they do, okay? 10, 18, 36, and 54, okay? Once again, if we just focus on these three here, we would say increase in melting boiling points. And in fact, guys, if I had to say, if you want to rank these in order from lowest to highest melting points or boiling points, we're doing boiling points, but it doesn't matter, you would say this would be the lowest, this would be the highest, and those two would come next, yes? So if you wanted to go from, let's say lowest is number 1, this would be 2, 3, and 4, yes? In order, lowest to highest, okay? Yes? Now, is that in fact true? And the answer is yes, it is, okay? I'm actually just going to get rid of some of this stuff so we don't get too confused here with different colors and whatnot. Let's do some green. Here we go. H2O, H2S, H2SE, H2TE. Okay? So you can see out of those 4 which one the strongest is. It's most certainly water. Has the highest boiling point or melting point, which is an indication of how well intermolecular forces hold together. Yes? Okay? Here's the 3 that we talked about. Increase in size means increase in melting boiling points. Yes? Look, hey, is hydrogen bonding stronger than dipole-dipole? In this case, yes it is. In most cases, yes it is. If there was no such thing, look, you might say, I still don't believe you, Mr. Bachek, about the hydrogen bonding thing. Why do we have our own category? Because isn't hydrogen bonding this special dipole-dipole? Aren't you just making stuff up? No. Look, if there was no hydrogen bonding, do you agree that water is still polar? Would it still be dipole-dipole? Absolutely, yes? Look where water would boil at. About minus 80. Yes? Guess what? That's kind of a problem. Because all the water that we would have, there would be no lakes or rivers. To drink water, you'd do this. Because it would be in gas form. True? Because it would have boiled at minus 80. So there'd be no lakes, there'd be no rivers. We'd gulp water vapor. Yes? Okay? But it's not. Thank God for hydrogen bonding. Huh. Catholic school and all. Look. That's a difference of 180 degrees Celsius. Does hydrogen bonding need its own category? Most certainly it does. Because in this particular case, it's 180 degrees stronger than where it's supposed to be. If it was just dipole-dipole, there's a big gap there. It's not. It's hydrogen bonding. It's 180 degrees stronger. That's substantial, okay? I don't know why you guys packed up, because you still got some notes to take here. So, this is the most important thing I'm going to tell you here. Okay? You guys have this in the square now, and you're going to fill this in. Okay? I will move this actually over here, and we'll move this down here a bit. Okay. So I'll let you guys copy this. We're not quite done yet, guys. Just wait. So, look, the reason I know some of you guys are still copying, but ionic metallics at the top, because they're the strongest, right? I showed you that chart. You can see that they're equally just as strong. If I say which one's stronger, you say, I don't know. Ionic and metallic are both about the same strength. I don't know. There's exceptions both ways. When you get to molecular, hydrogen bonding tends to be the strongest. Then it's dipole-dipole, and the weakest, of course, is London. Well, London, of course, is based on size and shape. Okay? Notice, when we went over the questions, this is what I said to you. I said, is it? And this is what you guys should do, because I'm going to give you compounds to compare. Either 4, and you're going to arrange them, or 2, you're going to get a lot of practice with 2, and you're going to tell me which one's stronger and why. This is what you should do. Listen closely. Is it ionic? If it is, you're done. Okay, that's probably strong. I won't give you an ionic and metallic because it's too hard to tell. But is it ionic? That's what I asked you guys today. Is it metallic? If not, then you should go down to molecular. Is it hydrogen bonding? That's the strongest one. Is it dipole-dipole? That's a little bit weaker. Is it London? That's the weakest one. Keeping in mind that London forces do affect these two here. So if you have a dipole and a dipole, what are you going to do? Well, you got to go to London, right? Size and shape. If you got 2 hydrogen bondings, what are you going to do? Well, they're both dipole-dipole. They both have London, size and shape. Okay? Now, I'm going to ask you questions based on this, and it's really important that you have to know this. You have to be able to slot them in, because everything we do is going to be about comparing molecules. Which one has the higher melting boiling point? Which one has the lowest one? Okay? If I'm going to eventually, in fact, I'll do this probably at some point in time, I'll say, which one out of these 4 have the highest melting boiling point, A, B, C, or D? And I'll put an ionic compound in mixed with molecular ones. Well, guess what? When you go to do this thing, you say, is it ionic? Ionic. Any of these ionic? Oh, yeah, this one is. Well, guess what? It's probably the strongest one. Because remember, these are very, very strong. Big gap, quite weak, yes? Opposites attract, sharing. Weak, yes? Strong, like Arnie. Weak, like sharing. Okay? You need to be able to slot compounds into here. That's the most important thing, and compare them. Okay? So we'll talk a little bit more about that tomorrow.